GitHub Copilot writes your backend in 4 minutes. Cursor scaffolds your database in 2. So what exactly is your job now? The engineers still employed at Zepto are not the ones who write the fastest code. They are the ones who decided Redis, not PostgreSQL for inventory WebSocket, not polling for tracking dark store, not warehouse for fulfillment. Every one of those decisions is system design. AI cannot make them. It does not understand the 10-minute constraint. It does not know why one wrong choice collapses the entire promise. You are about to learn the mental model that makes those decisions obvious. 5 things you will own after this video. The complete 7-layer mental model, a diagram you can draw on any whiteboard in 3 minutes. The reason each layer exists, not just what it does, the constraint that forced every choice, the 10-minute SLA, and how it drives every design decision in the system. The exact judgment call AI misses when asked to design Zepto. And the survival skill, the ability to see the full system, not just your layer of it. If you watch this video to the end, you will be able to answer a system design interview question about Zepto better than 90% of candidates who have been building software for years. That is not a promise I make lightly. Let us build it. Start with the 2 client apps, the customer app on your phone, browse, add to cart, place order. The delivery partner app on the rider's phone receives order assignment, sends GPS every 3 seconds. And AI can scaffold both of these in minutes. What it cannot do is design what happens when these 2 apps talk to the same backend simultaneously at 100,000 requests per second. That is where the system design begins. Every request, from you placing an order, from the driver sending GPS, enters through the API gateway first. Think of it as the only gate into a secured compound. It checks your identity token and blocks bots. Nothing reaches the services behind it without passing this gate. Next to it sits the WebSocket server, the live radio channel that pushes order updates to your phone instantly. These 2 layers are the reason Zepto feels instant. Without them, every app would be polling, sending a request every second asking anything new, and the backend would be buried under 10 million unnecessary calls per day. The delivery partners app uses the same gateway. Everything goes through one entry point. This is a design decision, not a default. A junior engineer might create separate entry points for customers and partners. A system design engineer creates one. Because one gateway means one place for authentication, one place for rate limiting, one place to add security rules. Fewer moving parts, fewer failure modes. The gateway routes to the order service layer 5 and the brain of the system. Every business decision happens here. Which dark store is nearest? Are items in stock? Which partner is available? Write the confirmed order. Now here is the part that surprises most engineers. The order service remembers absolutely nothing between requests. Not your cart, not your last order, not your name. This sounds like a limitation. It is the opposite. Stateless means any of the 50 order service servers can handle any request. No sticky routing, no single point of failure. If one server crashes, the other 49 absorb its traffic without losing a single order. AI will generate a stateful order service by default. An engineer makes it stateless. That one decision is the difference between a service that breaks at 10,000 users and one that handles 10 million. The order service reads inventory from Redis layer 6a. And here is the single moment in this entire system where AI fails every time. Not because it writes bad code, but because it writes code that is 4 times too slow. Ask an AI to build Zepto's inventory check and it will query PostgreSQL. Clean code, correct result, 20 milliseconds. The 10-minute constraint gives the inventory check a budget of 5 milliseconds. 20 is 4 times too slow. Redis answers in under 2 milliseconds because it lives entirely in RAM, nothing on disk. This one judgment call, Redis not PostgreSQL for inventory, is the difference between Zepto working and Zepto missing its own promise. That judgment is system design. Write it down if you need to. This is the answer to 50% of system design interview questions about quick commerce. Confirmed orders are written to PostgreSQL layer 6b. This is the permanent durable store. Every order, user account, and product catalog lives here. PostgreSQL is ACID compliant. Every write either fully succeeds or fully rolls back, no partial saves. This is why PostgreSQL, not Redis, stores orders. Redis is fast but volatile. It can lose data on a restart. An order that disappears is a refund, a complaint, a lost customer. The right database for each job, that is a system design judgment call. After writing the order service notifies the WebSocket server layer 4. This layer exists because of one problem. Your phone needs to know the order was confirmed without you pressing refresh. Polling, checking every second generates 10 million unnecessary requests per day at Zepto scale. The WebSocket server holds one persistent open connection per active user. When the order service fires an event, the WebSocket server pushes it instantly. Zero polling, zero wasted requests. The WebSocket server pushes order confirmed to your phone. The server initiated this. You did not ask. The connection was open before you even tapped place order. This is the difference between a push architecture and a pull architecture. An AI scaffolding a mobile app will default to polling. An engineer who has seen this at scale builds persistent connections because they understand what polling costs at 100,000 concurrent users. Simultaneously, the WebSocket server pushes to the delivery partner's phone. New order, zero point 0.8 kilometers away. Both pushes yours and the partner's happen in the same second. The 10-minute clock is already running the moment both devices receive their notifications. This parallelism is intentional. Sequential would add 1 second. At Zepto's order volume, one unnecessary second per order adds up to days of lost delivery time per year. Here is the master insight. The 10-minute delivery promise is not a marketing line. It is an engineering constraint that forces every design decision you just saw. Inventory check must finish in 5 milliseconds. So Redis, not PostgreSQL. Dark store assignment must finish in 50 milliseconds. So geohash lookup in Redis, not a scan of 400 stores. Real-time tracking must reach the customer without polling. So WebSocket, not HTTP. Every layer you just saw exists because the 10-minute number ruled out the simpler alternative. When an interviewer asks why Redis for inventory, the answer is not it's fast. The answer is the 10-minute SLA gives inventory a 5 millisecond budget. PostgreSQL takes 20. Redis takes 2. That is the only calculation that matters. That is the architecture. Now let us walk through what actually happens step by step, millisecond by millisecond. When you tap place order 8 hops, everyone with an exact latency budget, it must stay inside. You tap place order. Your app sends a post request to the API gateway. The gateway does two things instantly. Checks your login token, checks your request rate. If you are a real user making a normal request, it passes. If you are a bot sending 1,000 requests per minute, it blocks. This is not optional logic. At Zepto's traffic without rate limiting, a single bot attack saturates the order service and every real order fails. The gateway routes to the order service. The order service is stateless. It stores nothing in memory. Every request starts fresh. This means any of the 50 order service servers can handle any request. If one server fails, the others absorb its traffic instantly. No request is lost. Stateless design is the reason Zepto can scale horizontally. Add more servers when traffic spikes without rewriting the service. Interview trap. Many candidates make the order service stateful, storing card data or session state in memory. This forces sticky routing and creates a single point of failure. Always make business services stateless. Every piece of state belongs in a database, not in the server. The order service checks inventory. One Redis command, ageGet, reads the stock count for each item. Redis answers in under 5 milliseconds. If stock is above 0, it subtracts 1 atomically, meaning no two simultaneous orders can grab the same last unit. Atomic subtraction is the technical term. The human meaning is two customers adding the same last bag of rice to their cart at the exact same millisecond. Only one gets it. The other sees out of stock. No oversell. Interview trap. Candidates often say use a cache without naming the operation. The correct answer is Redis edge gate atomic DCR under 5 milliseconds. Name the data structure, the command, and the latency budget. That specificity is what separates a system design answer from a vague answer. With stock confirmed, the order service writes the order to PostgreSQL. It records order ID, items, your address, and the nearest dark store. Now, how does Zepto find the nearest dark store from 400 options in under 2 milliseconds? Not a loop, not a query across 400 rows. A geohash, your GPS coordinates encoded as a short alphanumeric string matched to the nearest store by string prefix. The closest dark store found in a single Redis lookup. The entire database write, including that geohash lookup, completes in under 50 milliseconds. The order now exists permanently. Even if the server restarts, the order is safe. Order saved. The order service fires an event to the WebSocket server. The WebSocket server is a live relay. It holds an open connection to your phone and the delivery partner's phone simultaneously. It is waiting for exactly this event. When the event arrives, it pushes two notifications in parallel, one to each device. Three hops remaining, and the last two reveal the exact design decision most interviewers test on. Stay with me. Your phone receives order confirmed over the persistent WebSocket connection. No polling, no refresh. The 10-minute countdown appears on your screen. This notification was pushed by the server. You did not request it. The connection that carried it was opened when you launched the app, before you even search for milk. Simultaneously, the WebSocket server pushes to the nearest available partner, new order zero point 0.8 kilometers away. Both pushes arrive within 1 second of you tapping place order. This parallelism is the design decision. A sequential implementation, notify customer, then notify partner, would add latency and push the 10-minute clock closer to 11 minutes. Finally, the API gateway returns the HTTP 200 OK to your phone, the synchronous reply to your original POST request. All 8 hops done. Every component stayed inside its latency budget. The total time from tapping place order to seeing order confirmed. Under 1 second, that is what the 7-layer architecture was built to achieve. Now, I want to zoom into the one layer that surprises everyone. 3 databases sitting right next to each other. Most engineers would default to one. Zepto uses all 3, each for a different reason. Which data goes where, and what actually happens when you pick the wrong one that is next. Redis is the speed layer. Everything in RAM, nothing on disk during a read, inventory counts, session tokens, order state, geohash lookups, anything with a latency budget under 10 milliseconds lives here. The judgment call that matters. Redis data can be lost on a restart that is acceptable for inventory counts. You rebuild from PostgreSQL. It is not acceptable for orders. Those live in PostgreSQL. Right tool for the right job. That judgment is what AI defaults wrong. If this kind of decision making is what you want to be able to make confidently, subscribe now. Every Tuesday, one system design judgment call that keeps you relevant, free, no course, just the thinking. PostgreSQL is the permanent record, orders, user accounts, product catalog, pricing, everything that cannot be lost. It is ACID compliant. Every write fully succeeds or fully rolls back. When a product is not in Redis, a cache miss, the order service reads PostgreSQL and writes the result back to Redis for the next request. The Redis hit rate must stay above 99%. If it drops, every cache miss hits PostgreSQL and the database overloads. Maintaining that hit rate is an operational judgment. Another skill AI cannot generate. S3 and CDN handle images. Product photos load in under 50 milliseconds because they come from a CDN edge server close to you, not from the database. PostgreSQL stores only the image URL. The actual photo lives in S3, cached at edge nodes with a 30-day time to live. Images change rarely. A 30-day cache means 0 database reads for the most common content type on the page. This one decision removes millions of database queries per day. Redis answers in under 2 milliseconds because everything lives in RAM. PostgreSQL takes around 20 milliseconds. Disk reads and query planning. The 10-minute SLA gives the inventory check a budget of 5 milliseconds. PostgreSQL does not fit, Redis does. That is the entire calculation. Redis can lose data on a restart. That is acceptable for inventory counts. You rebuild the cache from PostgreSQL on startup. It is not acceptable for orders. A lost order means a refund, a complaint, and a lost customer. ACID durability is why confirmed orders go to PostgreSQL, not Redis. Redis holds everything with a short latency budget and an acceptable risk of loss on restart. PostgreSQL holds everything that cannot be lost and has more time to answer right database for the right job. That is the judgment call. Ask an AI to build Zepto's inventory check and it generates a PostgreSQL query, clean code, correct logic. 4 times over the latency budget. AI defaults to correctness. The engineer defaults to constraint. That gap is system design. You have now seen every layer, every hop, and the code trade off. Let us put it all together one final time. The full system in one clean view, all 8 hops. So you can close your eyes after this video and replay every arrow in order. Full system. All 7 layers visible. Hop 1. You tap place order. The API gateway checks your token and your request rate. Both pass, the request moves forward. Hop 2. Gateway routes to the order service. Stateless. Any server handles it. No sticky routing. Hop 3. Order service checks. Redis edge under 5 milliseconds. Stock decremented atomically. No oversell. Hop 4. Order service writes to PostgreSQL. Order ID items address nearest dark store via geohash. Under 50 milliseconds. Permanent record. Hop 5. Order service fires. Event to the WebSocket server. The WebSocket server is ready. It has been holding open connections to every active app since they launched. Hop 6. WebSocket server pushes order confirmed to your phone. Server initiated no polling 10-minute clock starts. Hop 7. WebSocket server pushes new order to the delivery partner's phone simultaneously. Both notifications arrive within 1 second. Hop 8. API gateway returns HTTP 200 OK. All 8 hops complete under 1 second. That is the full 7-layer Zepto architecture. 7 layers, 8 hops, 1 10-minute promise, and every single design decision forced by that one number. You now own the architecture. The last question, if an interviewer gives you 45 minutes to design all of this from scratch, no notes, just a whiteboard, what do you do in the first 5 minutes? The answer changes everything. That is next. 45 minutes, a blank whiteboard, an interviewer watching you. Most candidates start drawing boxes immediately. That is the first mistake, and it costs them the offer. The 5-phase framework that survives every system design interview. Phase 1, requirements. Open with the constraint. 10-minute SLA, 100,000 concurrent WebSockets, 400 dark stores. Do not draw anything until you have said this number out loud. The interviewer is testing whether you know which constraint drives which choice. Every design decision you make after this must trace back to the 10-minute number. 10 million orders per day, 100,000 concurrent WebSocket connections, 10,000 SKUs per dark store across 400 dark stores. These numbers justify the choices you are about to draw. If you skip scale, every choice looks arbitrary. With scale, Redis is the only answer. Without scale, PostgreSQL sounds fine. Draw the 7 layers. Trace one order end to end. For every layer, name the constraint that justified it, not just what it does. The gateway because you need one authentication point. Redis because the 5 millisecond budget eliminates PostgreSQL. WebSocket because polling generates 10 million unnecessary requests per day. The interviewer is scoring you on the why, not the what. The interviewer picks one deep dive. Most pick inventory caching. Explain Redis edge atomic decrement, cache miss fallback to PostgreSQL, and why the hit rate must stay above 99%. If they pick dark store assignment, explain geohash. If they pick WebSocket, explain the upgrade handshake and how you route messages by order ID to the right open connection. Name the three core trade-offs before the interviewer asks consistency versus latency for inventory. You chose speed, accepted that a restart requires a cache rebuild. SQL versus no SQL for orders. You chose ACID, accepted slower writes. Push versus polling, you chose push, accepted persistent connection overhead. The interviewer wants to hear that you understand the cost of every choice. That is what survives the AI era interview trap. The most common failure is saying I would use Redis because it is fast. The correct answer always names the constraint. The 10-minute SLA gives inventory a 5 millisecond budget. PostgreSQL takes 20, Redis takes 2. That is the only calculation that matters. 7 layers, 3 storage systems, Redis for speed, PostgreSQL for permanence, CDN for images, 8 hops from tap to delivered, 1 constraint, 10 minutes that forces every design choice. Here is the before and after. Before this video, if someone asked you why Redis for inventory, the answer was probably it's fast. After this video, the answer is the 10-minute SLA gives inventory a 5 millisecond budget, PostgreSQL takes 20, Redis takes 2. That is the only calculation that matters. That shift from it's fast to the constraint forces it is not a small thing, it is the entire difference between a developer and an engineer. And in the age of AI that writes the fast code for you, that distinction is your job security. You can draw this system from memory now. That is the skill that survives. Next Tuesday, real-time order tracking. The GPS dot on your screen moves every 3 seconds. Every single one of Zepto's 100,000 active users watching their order. Now here is the question. What does an AI generate when you ask it to build this? It generates HTTP polling. 1 request per second per user at 10,000 concurrent users, that is 10,000 requests per second on your backend for 0 new data, 90% of the time. An engineer who has seen this at scale builds WebSocket. 1 persistent connection server pushes when something actually changes. That is episode 2. The upgrade handshake, the dual client channel, the exact failure mode polling creates at scale. See you Tuesday. Subscribe to ByteLearn for the complete 1 engineer system series, 1 survival skill per week, every Tuesday. If you are a B.Tech student, a fresher, or an engineer worried about what AI means for your career, this series is built for you. Hit the bell. See you Tuesday. Question: which of the 7 layers surprised you most? Drop it in the comments. I rate everyone.